Anyway,
Yeah. In the future, we would have this as a GitLab repository that everyone could reuse, right?
yes. This one I'm actually thinking about turning into a repository.
Okay. Like in the toolbox would be great.
Yes.
Just messing with you.
Yeah, I know.
Okay, folks. Today we have Nathan doing a follow-up on his presentation on small area forecasts. Thank you all for joining. Nathan, take it away whenever you're ready.
Okay, thank you. So today the idea is to put in practice what I explained last week, which is small population forecast. So I explained a couple of methods that can be used for population forecast or population projection. The best term is projection, but anyway. And I showed in the last 5 minutes two functions that I've created to uh, both project arithmetic, geometric, and AIVI populations. Today, I'm going to show step by step how we can do that without the functions because it's not something that needs to be difficult or depends on a function. We can create those projections based on simple numbers. So the idea here is to show mathematical methods because they are the best ones when we don't have any resources. And then the Hamilton-Perry one, because it's the best one when we want to project the stratified populations by age, sex, race, gender, or any other stratification we might want. So I'm going to show you how to simply calculate those on R. So the idea here is I just copy paste. So this actual package we won't use. We can, of course, but we won't. Um, the idea here is to just go through how it actually works. So we're going to start with the mathematical methods and with the arithmetic. I put the white background here because I think it's easier to see. But if it's too small, just let me know and I can zoom in a little bit. So the arithmetical formula is based on a linear trend. So this means that if it's 1 today, tomorrow will be 2. The next day will be 3, and the day after will be 4. This is a linear trend. And this assuming is basically what we do for almost everything because arithmetical are usually what we do when we don't know anything. That's something that we do for regressions. If a data set has continuous variables, we will assume is a normal distribution. Therefore, we're going to use a linear regression. We test for normality. If it's normal, we stick with linear. If it's not, then we change. For population projections, the same. We start with the arithmetic because we assume that it's a linear trend, it's normality. And the base of arithmetic method is the population at the year to be projected equals to the population at year 0, a coefficient of projection multiplied by the year of projection minus the year of the census. That means that we want the population at year t based on a population at year 0 and another population. So we need at least 2 points here. We need like 2010 and 2020 census, or in Brazilian case, 2010 and 2022 census, because it will allow us to project based on a past trend. For the coefficient of projection, Ka, it can be calculated as subtraction of population at the second time and the population of the first time, the first point. The same goes for the years. Let's go to an actual number thing, because I think it's easier when we see with actual numbers than with the formula. I will use Durand's population. I got it from Wikipedia, so I'm assuming it's right. Durand's population at 2000s, it was 187,000. At 2010, it was 228,000. And I want the population at 2020. So what's my population at 2020? I don't know. The population at 0.0 will be population at 2000 because it's my the first last. Population at time 2 will be 2010. T will be 2020 because it's the population I want, the year that I want. T0 will be 2000 and T2 will be 2010. So what we do, the formula, I'm going to use this as, and then create it with you. The formula is to get the population at a certain time, this meaning population at 2020, we will need the population at 0.0, meaning that 2000, it's 187,035. And this will be added to a lot of things. This is the coefficient now of trending. This coefficient stands for the population at the second time. So 2028, 130 minus 0.35. So this is the first time, the first part, and it's divided by 2010 minus 2000. So what it's doing here is creating a coefficient based on past trends. And this is a linear. You can see that I'm just using the same data points. So the population at 2010, the population at 2000, divided by the difference between 2010 and 2000. And this will be multiplied by 2020 minus 2000. This is to calibrate and give us the actual difference in time, because here we're differentiating in 10-year period, but we want a 20-year period based on 2000. With that, we can just run. And we get that the population in 2020, following the arithmetical trend, will be 2069, 625. This is close to what it actually is, because according to Wikipedia, it's something like 283,506. So it projects based on a linear trend. Of course, it can be off from the actual numbers because it's dependable on a lot of things. It depends on whether we have more deaths or less deaths. It depends if we have a fertility rate that is higher or not. It depends on migration. Durand's case, there's a lot of migration happening, especially on those years between 2010 and 2020, because of the research triangle and the moving of a lot of companies to the research triangle. So of course, this will be a little bit off, but it's useful because those 20,000 people, it will do a difference, but it's not something that will be too way off that we cannot use for our research. So this is a simple method that we can use to calculate the population and a linear trend. Another way is the geometric one. The geometrical formula, it's similar. It assumes a coefficient of projection, a coefficient of growing, but this is based on a compound rate, so it's not a linear trend. That means that the population needs to be in a curve, not in a straight line. And for that, we need a more sophisticated formula. I'm not going into too much the why we use what we use. Instead, I'm just going to show you how to do that. So this goes almost the same as the linear trend, but we have some differences. First, the population at year t to be projected equals to population at year 0 multiplied by the exponentiation of the coefficient of projection multiplied by the difference of years. You see that this stays the same, the coefficient multiplied by the difference of years. But here we don't have the plus that we have here. We're multiplying, and this is a exponentiated. And we did that because it's a curve. So we need to exponentiate to get this curve going. This coefficient, it will be the same thing as the coefficient for the arithmetical, with the difference that we need the log of the population, because it will smooth and create this rate that is not trending linearly, but rather compounding, more like a parable. So we will use log the population. So population at the second time, like 2010, will be the log natural minus the log natural of population at time 0, which is 2000. And then we'll divide this by the subtraction of those years. That means that for geometrical, the population at given time will be this huge formula. But this is simple, since it's only a couple of subtractions and this is a log on only 2 terms. Let's go with an example for the actual numbers. So I'm going to use Duran again. So the same things, the same population, and the same year that we want. It didn't change anything, but now the formula is a little bit different. So let's do this. Population at time 0 will be 187,035. And this is multiplied by the exponentiation, and it already creates a parenthesis. I like to do this to create the rest so I don't get confused. But of course, if you're copy and paste, is a little bit easier. So first thing I need is log of the 2010 population, 228,330, minus log of 2000 population, 187,035. And this must be done before it's divided. So I create a parenthesis, divided by 2010, the second data point, minus 2000. And this must be made prior to the multiplication of 2020 minus 2000. And this must be made before the exponentiation. So now we have the exact same thing. Little bit confusing, I know, but once we do that, we will get the population that is 278,742. This is way closer to the actual number. That indicates that Durham's population is expecting to grow more in a compound rate rather than in a linear rate. In this case, it will be better to use the geometric one. How do we know that? Usually we go for a constriction. That means we use a higher level population like North Carolina or Durham County to adjust. I'm not going to explain this here because it is another method that is the AIBI. But this is a couple of useful methods when you don't have any specialized data, when you have any data that is divided or stratified, and you need more rapid or basic projections. This, of course, can overestimate in small cities or small areas, because if we assume that it's one person here, it will be two person tomorrow. And of course, one person cannot generate two. That's unlikely. But it's also useful because we won't have like one. We usually don't. So both work fine, really fine. Geometrical usually works better, especially for those medium to high population cities. Like Durham, like Raleigh, and Chapel Hill. It won't be good for like New York City, because New York City is huge. Or like São Paulo, that is also very huge and is bigger than a lot of countries. We do that to São Paulo anyway, because it's still a city inside Brazil, and it's dependable on Brazil's population. But it's good to know that those two, the mathematical methods, work just fine if you need it. So if you don't have a population for a certain period of time, you can just use those mathematical methods. But if you do want a population that is closer to what we actually have, we can use the Hamilton-Perry method. So I explained this method in the last section, and I'll touch it a little bit more deeper today because it's the best method we have to do population projections and forecasts. Why? The HP method, the Hamilton-Perry method, is based on cohort changes. That means that mortality, fertility, and migration are automatically implied. Because what's the golden standard for projection? The cohort one. We use the mortality, the fertility, and the migration to actually project something. But if we don't have those data, especially based on age groups or race groups, ethnic groups, we need something that is implied. And the Hamilton-Perry does that. And how it does that? The first thing we must do is to calculate the cohort change ratio. And this is an age group in time 0 divided by age group in time 2 plus the difference in years. What it means. In 2010, I have the population of 10 to 24, to 10 to 14, sorry. And this population is 1,000 people. In 2020, 10 years apart, that population have grown, have aged 10 years, so 10 to 24. 20 to 24. And the population is 950. That means that the cohort change ratio is 0.95 because we're dividing the population that actually survived by the population that we expected that survived. Because we expected that those 1,000 people would be here 10 years later. It was not. It could be grown. It could decrease. It could be the same. So this is why mortality, fertility, and migration are implied. Because if it birthed more, it will be here. If died more, it will be here. And if it changed location, it migrated, it will be here. It's already implied. Because mathematically, the cohort change ratio approximately means survival plus net migration. And then to project, we multiply the cohort change ratio to the most recent population. So the population in 2025 will be the population in 2020 multiplied by the CCR. That means 950 multiplied by 0.95. This will give us 902 approximately. Of course, we don't get 0.5 people. And this number will be the population of ages between 25 and 29. Why? Because I'm doing a 5-year projection for this population. So these have aged 5 years. So this population have aged 5 years. So 20 to 25 will be 902. So this is the best method we have to project any population because it accounts for any differences that we already have automatically. We don't need those data. Let's do that for Maringá. So this is the city I live in. The population of 10 to 14 in 2010 was 248,000. Oh, no. 2,400, 824, and 27. What's happening to me today? I can't read anymore? Am I dumb? The population in 2022, 10 years apart, and I'm doing 10 years as an approximate because it's a 12 years difference, but I'm going to use this just a proxy to exemplify, not to actually do the calculation. It's 31,906. That's one first try. And I want the same population in 10 years apart. So I am following the same people in 20 years, 2010, 2022, 2032. How we do that? We do that by dividing the population in 2022 and the population in 2010. It gave us approximately 1.88, that 28. We can round this up. We don't need to use the entirety, but we can if we want a more precise. Then we project. Population in 2022 multiplied by the population, the cohort change ratio. And that gave us 40,839.68. So it will be 840. We can, of course, use the total here, and will give us a little bit more. Either way is fine. If you want a more accurate, you can use the whole number. If you want to round it up, it's fine. Why we do this way? So I saw João Vitor's Borges message here. We do that because it's a change radio. So we get the most recent and divide that both for the last recent. I'm not multiplying by number scales. I'm multiplying by time scales. So I'm dividing by time scale. So I need to divide the most recent population and then by the most old population. That's why I'm using this, because this is a rate of cohort change. So it's a change between the most recent and the last recent.
Thank you. It's because like the CCR above the place you're now was like written T0 divided by T2 and not the opposite, like you explained now.
Oh, it was just a typo. So it was just a typo. We divide the most recent for the last recent one. So that way we can get to what we expect to be the closest population for Maringá at the age 30, 35, 30, 34, this interval. Why we do these intervals? Because it's what we are creating here as the CCR. If we want to project based on like annually, year by year, we need to create a yearly CCR, which is a little bit different, because then we need to project based on the dividing modulo of CCR for each year. It's a little bit complicated. I'm going to show this because it needs more 3 or 4 steps to create this by yearly. But it's something possible. It's something that we can do definitely. But there is one thing that is a little bit different in this method, because we're growing people, we're aging people. How we're going to age something that doesn't exist? Like people that are born, they're born with 0 years. We don't have like people with -2 ages. How do we project something like that? Does anyone know? Does anyone have a insight of how? Birth expectation, but how do we create a birth expectation? It's based on what? Some sort of censorship? Not so. It's more like a birth expectation, but based on the woman's rate and the amount that we have of a child now. It will be children per woman. So since we don't have actual change in cohorts, we use child-to-woman ratio. So we create, for a given time, the children, like 0 to 4, I'm using a 5-year period here, and the women in between 15 and 49. This is the fertile age, reproductive age, something like that. The age that expected to birth, the women expected to birth, because more than that or less than that are not the best. Not that 15 is the best, but anyway. So this create a child-woman ratio, and then to project, we multiply this child-woman ratio to the population of women in future years. then we can get like this. In 2015, children of 0 to 4 years are 200. Women in the fertile age are 2,000. 200 divided by 2,000 is 0.1. This one has no other cases because it's pretty obvious, but to project in 2020, 5 year, we will use the women in 2020 for the same age. So I have a growth of 100 women, and I'll multiply this for the child-woman ratio, so 2010. So we expect to have 2010 children from 0 to 4 in 2020. So this is more based on the women and the children per women than in a aging group. So this is useful when we don't have the ability to create those aging cohorts. This is something that we do when we don't have the population. A couple of notes on this matters. If we have the birth per year, we can also use this one to create, we can use this one to project. It's not every city and not every county or every state, country that has this publicly available. Brazil has the birth registry, so it's publicly available. We have every single year the amount of births, so we can do the Hamilton-Perry, the pure Hamilton-Perry to project. It's not something that is wrong, but if we don't have the actual change in cohort, we can use this one to project an expected number of people of age 0. Another note is that if we have a 0 in a population and then it's grown, it will give us a wrong result. Because if we have here 0, for any reason, I would need to do this. That doesn't exist. So for small areas like this, we usually do one of two things. We give a rate, an epsilon rate, that can be just slightly at 0, but not 0, like 0.5. So it will be like 10 divided to 0.5. But this gets way big. The cohort change ratio gets bigger. And then it seems like we're overestimating, which we are. But if it goes from 0 to 10, it's expected to go to 20. Another way that we can do that, and we need to do, is spatial smoothing. Spatial smoothing will be just like we do for our rates when we're doing spatial analysis. We're going to use a Queen method to use the neighbors mean the average growth, or CCR, to then create the projection. This is useful because small municipalities or small areas that have like 0 or close to 0 population, or even if you're talking like São Paulo that has 20 million, I think, and cities around São Paulo that doesn't have the same amount, they're like 1,000 or 10,000, it will create a disparity that is too big. So we want a smoothing that will allow us to really create a projection that is based on real geographic and demographic scenarios. So we usually smooth that by Queen methods, which give us like a very, very useful number. Together with this, we can do a Bayesian smoothing. So is the empirical base, spatial base rate, because it kind of aggregates everything. The Bayesian thing here is very useful because population behaves more Bayesian than classical statistical. And another thing that we want to do sometimes is create this and compound by and constrict by a higher level number. So if we gonna project something and we know that it will create an instability on the state level, for example, we want to adjust these numbers by the state level numbers. So it creates a constriction that it's more related to the real scenario. So this is the how we can create those populations. My idea now is to use the Hamilton-Perry method to create the population for stratified by race color because we don't have it. It's usually not hard to do because I just showed you that it's not hard, but it's not useful for most of the statistical bureaus. But for research, it's very difficult for us not to have it stratified by race, color, or ethnicity. So my idea now is to get this Hamilton-Perry method and project stratified by gender, age, and race color in Brazil by municipality for the next 12 years. So from 2010 to 2032. And then put it in a, I don't know, like a toolbox so people can use it. So that's why I wanted to show this. If any one of you have any questions, if you didn't understand something, just let me know.
Awesome, Nathan. Thank you. It's nice to see the math behind the functions there and see it kind of works. The question that I had is that if you could give a few examples on projects that folks could use this, and if there are any rules of thumb, like should you use all of the methods and compare the results? Should you choose just the IBI one or something for folks to get started?
Okay, so rule of thumb, if you have the official numbers for the population you want, use the official numbers. If you don't and you need to project, it depends on quality of data. If you have very, very, very low data, use a mathematical one. It doesn't matter which one.
And
If
by
you
low,
have
do you mean granularity of data or quality of data? Or
quality
maybe
of data.
even time spans, I don't know.
Yeah, one thing that is important is that you can only project based on the amount of time you have. So I'm projecting here from 2000 to 2010. So the maximum that I can guarantee of a good projection is 2020. If I do 2022, it will be a projection. I will have that number, but it won't be reliable because I'm not in the last in the period of time. So that 10 year span. And when I say like very low quality, I say quality of data. So if you cannot trust that data that much, or if you don't have access to a stratified data, you want to use a mathematical method. AIBI method is usually not something that people do outside Brazil. I discovered that recently because it's very old and Brazil started using it a very long time ago. And the other countries use other forms of projection because they usually don't have the necessity to do census in such long periods because they're not that big.
I see.
So they can do like some countries do it annually. Brazil could never because it's too huge. So only big countries will use AIBI methods. The other ones use the cohort one or Hamilton-Perry ones because they have the data.
Okay. And then a follow-up to that is, so I've seen folks doing when we didn't have the most recent census for Brazil, for instance, folks would use the 2010. Even when you have data for the condition of interest, let's say you are studying HIV, you have a better reporting system that you actually know how many cases were reported year by year, right? So from 2010 to 2020, you know year by year the number of new cases. And I've seen folks using a static number for the population, so the census for 2010, for doing their estimates for incidence and prevalence, etc. When we do these projections, as you're explaining, I see that they bring a level of uncertainty, and that's assumed. Some of them are going to have higher error, lesser error, etc. Do you personally see the value of adding this level of uncertainty because it's going to address some of the limitations of using the data from 2010? You know what I
Definitely.
mean?
Yeah, because the uncertainty will be there anyway, because you're using the same population for 2010 to 2020. It's not, definitely won't be. So it's more useful and less uncertain to use a projected population than a static that is based on 10 years ago. If it's 1 or 2 year period, it doesn't matter. But 5 years or more, you need to do a projection, because if you do a static one using just the population of 10 years ago, it will be valid, the result will be valid, but it will have a uncertainty that won't be great. You'll create a lot of bias. So using the projected population, there will be an uncertainty level that is less than the using the static one. So I see this as a must choose for any epidemiological thing that we do that needs population for more than a 5-year span.
I see. Nice. Thank you.
João Vitor, do you want to?
Sorry, it's just I have a doubt. In the end of your explanation, you are using the 10 divided by 0.5, the coefficient. I didn't understand very well the explanation.
Yes. So let's think of a area where we don't have anyone. And then let's assume like a new neighborhood appeared. So the city grew and the new neighborhood appeared, right? So that new neighborhood will have an amount of population, a very small population, but because it's a new one, 10 years ago, it didn't exist. So what's the population 10 years ago? 0. Can we divide the current population by the past population. No, because we're dividing like 200 by 0. It didn't exist. So what we can do two things. First, we create a coefficient, a mock coefficient, that will give us a number to divide to. So in this case, 0.5. Why that? Because this is 10, so it's very small. But if I'm doing 200, I can stick with 0.5. What happens is that when I multiply, it will give me a very, very large population. It's not accurate. We can do here is divide by a number that appears to be a good amount, 4. This is more simple. So we divide by a number that creates for us like a possibility. So we can create a cohort change radio.
Okay, thank you.
Any other questions? I know this is very like mathematics, calculus 1 sort of thing. And I hope you stick to the end and kind of not hate me for explaining this in too much detail. But it's very useful and I like it a lot. I'm a nerd.
This was great.
Oh, sorry.
Go ahead, Guilherme. I was just going to comment for Nathan to make this available for other folks to use in the future as well. I made a joke about the repository, but I really think we should have this on the toolbox
Yes, me too.
Sure.
available. Go ahead, Guilherme. Sorry.
I'll try to make sense because I don't know exactly what I want to ask, but it's a question I have. When you consider, for example, a few years ago we had COVID here in Porto Alegre. We had a flood, I think 2 years ago, and I've began to think, okay, that probably affects the ratios that you would use, but in my mind, when you start to understand that happens so often nowadays, I don't know if that actually affects the end result. I don't know if I can make myself clear.
Yeah, you did. And it's a great question. Mathematical methods cannot account for that. And that's a problem, of course. And if we consider COVID to be 2021 and 2020, 2021, 2022, it's going to be hard for us to account for that, but we must do because a lot of people died. That's one thing that Hamilton-Perry does. It doesn't matter because it's already implied. We already have the population. So, of course, 2010, 2020, here, we're still in the middle of pandemic. So if we're projecting to a 2030, it will give us a slightly higher number or a slightly lower number. But since it's already implied for mortality, it's a useful method. So that's a good thing about the Brazilian census because it was in 2022. So we do have a more accurate one based on COVID. So it's easier for us to project those population more accurate considering COVID because it's already implied with the mortality, the fertility, and the migration that barriers that COVID implied. So mortality grew, fertility grew a little bit as well, and migration did not. So this is already accounted for in the Hamilton-Perry method. Of course, if you do have this information, mortality, fertility, migration, you can do the cohort one. So the another one, not this one, which is the gold standard because it counts exactly that. But if you don't, then this is the best method that already counts for that. And it's a good projection also for population when we need to do studies on epidemics or pandemics because it gives us a more real scenario. So this is a good one to create those small area that can be affected by a pandemic or an epidemic.
Thank you.
Did it make sense? Okay.
Yeah, man.
All right, folks. If nothing else, let's thank Nathan for the great presentation and the follow-up on the theory. It's nice to see the theory and the methods, the practice side by side. We are happy to have you sign up for other presentations as well. So you heard João Ricardo on the meeting this Monday, yesterday, talking about how we are expecting folks to present at least once in these meetings as you are part of the affiliated with Gemini. So keep an eye out. We're gonna reach out to you and ask for those presentations. Before we wrap up, I do see that Timothy shared a question. Sorry to cut you off. Maybe Nathan, you can answer that.
Yeah, I was answering the chat, but population at extinction. This is something that we can do. We can project, of course, and then expect 0, but it won't be reliable because we actually don't know. So because there's a lot of noise on that. We have pandemics, we have war, we have hungriness, starvation, we have a lot of diseases, we have a lot of things that change that. What we can do is use like this for certain countries that already have a fertility rate lower than the, how do we say this? The minimum necessary to continually have people like South Korea. If we do this, the projection for South Korea, we can definitely have a projection that will give us a approximately, not exactly, but approximately year that people will stop existing in South Korea because the fertility rates are very, very, very low now. So it's lower than what we need to still having like population. So now people would just die and die and die. So that's it. That's we can do that, but that extreme, but it won't be too reliable except for a couple of scenarios. That's it.
All right. So thank you all folks for joining. Thank you, Nathan, again for the presentation. Let's meet again next week.
Bye, everyone.